So there's a number of kinematic relationships that we can establish for angular motion, rotational motion, um, in angular units, in angular quantities, that will be completely analogous to the relationships you've already established for motion using Cartesian coordinate axes. So for example, we've already established here that we're going to measure our position in terms of an angle. And that means our displacement will be measured in terms of a change in angle or a change in theta. That's an angular displacement. Okay, well, if you're moving, then that is occurring while time is passing. And to get a measure of velocity or an angular equivalent of velocity, we would simply take that angular displacement and divide it by the passage of time, which is to say this new quantity, omega, which looks just like a funny W, is defined as a change in angular position or an angular displacement divided by an amount of time. These are still vector quantities in that they care about direction and size. In this case, you have two to go around a circle, you have two choices of direction. Our convention will be that counterclockwise, counterclock, by convention will be the positive direction, which makes clockwise the negative direction. You can, of course, work outside of the conventions, but you have to always be self-consistent, meaning once you pick a direction to mean one thing, you have to self-consistently apply that to all vectors that could have directions along a circle. So we'll stick with counterclockwise being the positive direction in this case. So then our previous example with the circle showing the counterclockwise arc length, so the counterclockwise angular displacement, that would be an angular displacement in the positive direction. And so this is then this expression we just wrote. That's angular velocity. And then if we can have angular velocity, well, then what happens if our angular velocity changes, meaning the speed with which we travel around the circle changes, or the direction? That would mean we must be able to have an angular acceleration, just like regular acceleration, which was defined as a change in a velocity over a change in time. Then an angular acceleration must just be defined as a change in an angular velocity divided by a change in time. So that is then angular acceleration. So we have the same types of relationships, we've just given them different symbols to denote that we're expressing angular quantities of position rather than Cartesian coordinate positions of, values of position. All right, so we now have angular displacement, angular velocity, angular acceleration. Well, all of the same relationships we developed for regular old translational motion, for relationships between position, displacement, velocity, and acceleration, will all still be equally valid. We just have to self-consistently apply the angular equivalent quantities. What do I mean? Well, we had an equation for constant velocity that shows up on your previous tests and quizzes. And what does it say? it says that whenever you have a constant velocity, your final position, in this case, angular position would be a theta, is equal to your initial position, in this case, that's an angular position, plus whatever that constant velocity was, in this case, that would have to be an angular velocity to be used perfectly analogously. So that's a constant angular velocity times the amount of time that passed. So that is the exact same relationship you already had for translational velocity, just applied to angular quantities. You also had some relationships for constant acceleration. And in this case, if we want constant angular acceleration, then we just have to apply those same rules to the angular values that take their place. You had three rules. One of them said that your final velocity, so that would now be a final angular velocity, will be equal to your initial velocity, so that would be an initial angular velocity, plus whatever your constant acceleration is, that would now be a constant angular acceleration, alpha, times the amount of time that passes during which you have that constant acceleration. A second equation that we had told you how to figure out your displacement. In that case, your displacement, which would have to be an angular displacement if we're comparing angular quantities, so delta theta is an angular displacement, is equal to your initial velocity. That would therefore have to be our initial angular velocity, multiplied by the amount of time over which you have a constant acceleration, plus 1/2, whatever that constant acceleration was, multiplied by however much time passed, squared. And finally, there is a third equation that you could use in situations where you didn't know how much time passed, so it's time independent. And that just said that your final velocity, angular in this case, squared, must be equal to your initial velocity, in this case angular, squared, plus 2 times whatever constant acceleration you might have had during some period of time, multiplied by whatever displacement you had. In this case, it would be the angular displacement you experienced during that time. And that's your three constant acceleration equations, which are completely analogous to the ones you've already learned, just substituting the angular equivalents of each quantity type: displacement, position, velocity, and acceleration.